Thank you very much. Okay. Next. Can I have my first slide? Okay, I'm going to tell you about the London 2012 Olympic Velodrome. I'm English, so I have a slight advantage. This project actually started in the late 1980s. Next. Do I have a remote control? Sorry. Yeah, this project started in the late 1980s when I was working in Milan with Giancarlo De Carlo, and we had a number of projects where we were trying to make sports buildings fit into their context. Too often, sports buildings are great big boxes like this. And we worked on a palestra in the Venetian lagoon on Mazzorbo, and we tried very hard to make this building fit into the flat landscape of the lagoon. We also went on to develop a building in Siena, which only partly got built, where again we tried to make this fit into the Colle Sienese, but we were working very much in two dimensions. We were working with wooden beams, and the building was a cross-section which we tried to modulate. This project I've done in London has been much more three-dimensional. We have much more technology available and more sophistication in how we build buildings. So it was a terrifying commission because the English are very, very good at cycling now on the track. And when we came back from Beijing, the English cyclists had a phenomenal amount of medals. And we were told we had to make this velodrome the fastest, the best in the world. And if we failed, then England wouldn't get gold medals. Britain wouldn't get gold medals. So we set out to make the fastest possible velodrome in the world. And we went back to the science of this and looked at the 5 things we could do that would make it very fast. The first two, the athletes and the track, we don't have much control over that. As the architect, it's outside our control. You just have to hope these athletes are behaving themselves, and sometimes they go well beyond their means. So, if we start with the track is not standard, it's not like running. It's 250 meters, but there's different designs. And they're either shorter and fatter or longer and thinner. And we worked out that Ron Webb, an Australian, made the fastest tracks, and they're slightly rounder, so he has more world records. The track is made from 850 trusses that are 750 millimeters apart. They're 7 meters long, they're straight, and they change their angle as they go around. It's a bit like designing a boat. Every time he just slightly changes the design to improve the geometry. The pieces of wood, which are 40 by 40 millimeters, are nailed on by hand with 350,000 nails, and this in 4 weeks builds up the surface of the track. Laid on by hand. Very, very beautiful thing. No expansion joints, so it constantly moves around. And here's this final surface. If you've never seen a track, it's the most wonderful thing. And our ambition, in a way, was everything about the project had to focus on the track and, in a way, capture the spirit of the track. It's so beautiful. How could the architecture emulate this incredible geometry and dynamism of the track? So we had what was, in theory, the fastest track in the world in terms of its shape. But we wanted to make the atmosphere very fast. What you might not realize is that when you have track cycling indoors, you can control the temperature. If you make it hot, the air gets thinner, a bit like in here, and you can go a bit faster because you're pushing against less molecules, so there's less resistance. So we did a piece of research going back, looking at all the times of the tracks, the temperature, everything else. And unless you can go to La Paz in Bolivia and go very high, where there's very thin air, you need to really make it very hot. So we were going to aim for about 28 or more degrees inside, just for the competition, because London wanted to have more world records than Beijing, Athens, Sydney. All these Olympic cities are competing with each other. So we did a lot of studies, CFD analysis, on how to get that temperature high. And we had underneath in the middle a great big underfloor heating system, and we also blew in air from the outside. So we had a system of mechanical ventilation to warm this building up. And we could boost heat it, we could control the temperature, and we would stop cold air coming in at the doors. So the building had a series of gills on the outside. It could breathe air, it could blow warm air in. We had lots of warm air underneath. However, there's a real dichotomy here. The cyclists are going along at 60 kilometers an hour. They're going to feel cool, it's not too bad. The people in the crowd high up get very, very hot. So we had to control the temperature for the spectators and give the athletes the hottest possible space. So we did a lot of work on ensuring that the crowd would stay comfortable, that we could bring cool air in around the people at the high level. Meanwhile, the athletes on the lower level could go very fast in the warm air. And then we had systems for recirculation. We weren't just going to heat this air up and throw it away. We also know that the Olympics are in the summer, but this was going to be used in the winter in the future. So we looked at all the possible scenarios for how to heat this up in an economic fashion. So we built this fantastic track. We made it as hot as we could possibly want when you turn the thermostat up. And we had the elite athletes from Great Britain came and tested the track, and they thought it was absolutely fantastic. But we realized there was something else which could make it go much faster, and that was the environment of the crowd, the atmosphere. Because when we spoke to the athletes, normally what you have is the judges on one side, the public on the other side. As you cycle around, you get a big cheer on part of the circuit, then it goes quiet and you ease off. So we spend a lot of time working with the athletes to get the noise going all the way around. And we look, therefore, very, very hard at how we affect that. We put the crowd around the track. And these were the very first drawings we did, which was about focusing the crowd around this lower level and then having views out and an upper tier. So we worked very closely with models, and we put the crowd very, very close to the track and brought every single seat as close as we could. So this was the test event for the World Cup. And you see in cycling, it's very interesting. You can get very, very close to the track, to the edge. The drama is incredible. And the noise can be fantastic. So hopefully I have a little movie now. So this shows you the proximity we had. So this is the very furthest seat away at the back, and how we managed to wrap the seats very, very tightly around and make the cycling the focus for the spectators. There should be a little movie from the World Cup coming up next, which just gives an indication of the noise and the atmosphere. Okay, there's a crash about to happen now. There he goes. Okay, so we ran the World Cup, and they had a whole number of world records, and the athletes said the noise was so incredible that they had to almost hold back and not put all their effort into the first few stages. So they were starting to learn how to ride the track. But we deliberately studied all the acoustics. We took out the absorption. We made the space small and hard surfaces and had this incredible noise. So we got a fantastic track. We got the chance to turn the thermostat up and make it very, very hot. And we knew we could have a brilliant atmosphere inside with 6,000 people. The thing is, though, this was London. We were coming off the back of Beijing, where they had the most incredible Olympics with the Bird's Nest Stadium, which was the most amazing-looking building probably ever on television, just a complete spectacle. How does London and the Velodrome position itself in respect to this amazing piece of structure and engineering and art? Well, we thought, we really have to take a different tack. London is a completely different, established global city. It doesn't need to make this kind of noise. Could we look for a more sustainable approach? So we went back to Beijing and tried to build on London being a different approach. If you look at the steel weight in the Bird's Nest, there's 650 kilograms per meter squared. In their Velodrome, there's 85 kilograms per meter squared. We felt we should be demonstrating how you can have a beautiful building, fantastic Olympics, and using as little material as possible. So we developed this theory, which was based on the lycra of the cyclist, that we'd shrink the building and make it as small as possible. So we'd reduce the cost, we'd reduce the time to build it, and we'd reduce the embodied carbon. And we developed around the track, around the seating, a building that was so small that on the back seats you could almost touch the roof. We could not have made it even 100 millimeters smaller. So here you see the cross section, which is a catenary coming down 8 meters, the long section which goes up 4 meters, and we worked very, very hard with the engineers over months to get this elaborate shape. And we knew by having a complex three-dimensional shape between these two objects, we'd have a very interesting sculptural form. Here you see the steelwork. There's 48 trusses going up and a ring beam. The ring beam we managed to buy from the American gas and petroleum industry. Everything on the site, the concrete was as high a sustainable specification as you could possibly manage. So we have 48 trusses, and here you see the opposing two geometries and how this building is incredibly three-dimensional. And you start to get a sense also of the track manifesting itself in the form of the building. We then worked to work out how to clad this building in Western red cedar, and we did a lot of studies how to bring in the air and to get this geometry to work. But as you can see, there's a relationship between the track, the crowds, and the outside form of the building. And here you see it being built in the Olympic Park. So when you go to the end of it, it feels incredibly small, and when you stand under the side, it feels quite large. So we'd got this form that was very small, very interesting, and we knew we could reduce the carbon, but our mentality in the design team was to think about integrating everything in the design. Could we make it as efficient as a bicycle? The bike is the most ingenious invention probably ever. So we knew a double curving roof was very efficient on a long span structure. We didn't put photovoltaics and things on it because it was less sustainable to weight the roof down but they should be somewhere else. So we looked very strongly at the geometry, at the forms. We had to build this thing. We were under pressure for money. And the roof is a form of a torus. The outside is a series of intersecting cones. And we worked very hard to reduce the steel weight. So we started with our first concept and worked to the right and got 600 tons of steel out between the roof and the bowl. So we were all the time trying to make this a very efficient mathematical proposition as well as a beautiful proposition about how to make a building with as little material as possible. So here you see the roof with the 8-meter dip and the 4-meter rise. And so when it came to the structure of the building, we were trying to make it very, very efficient, and we set out to design it with a cable net. So these are cables. The whole roof is held up. It's 120 meters long, and it's held up with cables that are 36 millimeters in diameter. These are them being stretched. This is a diagram of the cables going on. This is it laid out, the pairs of cables. And there should be a little movie that shows how this went up in about 2 hours. Here's the fixings. They all had hydraulic jacks on. So it's a great system. There's no scaffolding. It's very quick. It's very safe. Can we run the movie? So this is just one morning, the roof getting pulled up into shape. So the outside is rigid. This pulls up. So it's a very, very exciting moment for everyone, very beautiful. So the Munich Olympics 40 years earlier had had a cable net roof. There's nothing new about cable technology, but this had to be insulated. We needed 300 millimeters of insulation on this building to make it efficient. So here's the cable net in place. The technical innovation was how to put a solid roof on top of a cable net which moves, and we invented a series of nodes. We invented a series of panels. We made the panels in a factory, very simple, very, very lightweight plywood, nothing complicated. And they just came in and sat on this roof, and we allowed all the movements to work. On top of that, we have a massive amount of insulation. So very, very simple, very honest, no dressing. And we made all the components in a very, very simple way. So this is the gut around the edge, just very simple elements of CLT. We mocked up everything, very good subcontractors. All these pieces arrive like a big jigsaw, a puzzle. And actually the building, we were under a lot of pressure for money. So the whole building is actually faceted. It's made up of a series of linear segments which join together. But actually we knew by studying the number of them that the final building, you would see it as a curve. And this sharp edge was very important. And then the outside was clad by hand with the Western red cedar all nailed on. These are the slots to let it breathe. So here's the final shape sitting in the landscape. And how do we compare then? Having done this exercise in terms of our steel weights, well, the Beijing one, which is also 6,000 seats, was 85. We were down at 30 kilograms a meter squared. So we had a fraction of the steel weight per square meter for the same brief. And if you look at Athens, because those tubes by Calatrava are so enormously heavy, that one is 250 kilograms a meter squared. When you compare the carbon story, say between Aquatics, the Bird's Nest, and the main stadium, the Aquatics and the Velo have a full roof over them, whereas the others are just stadia. We come out as a fraction because we have so little material in the building. So in terms of being scientific about it, working with the engineers to reduce, as our obligation should be, the amount of material we're using for all of these projects. How do you make something functional, beautiful, but with less material? In London, the Olympics were in the east. I like this picture. It shows the sun does sometimes come out in London. How do we make this building work in legacy when the children are using it after the Olympic Games? Well, we did a lot of studies on daylight. In the tournament, you need 2,000 lux for a competition. Just for training, you need 300 lux. So we did a lot of studies to get equal daylight just from the roof. So here you see no lights on, and you can use this building without using any electricity. It's very efficient to use. Meanwhile, in a tournament, this is the World Cup, you turn the lights on and have 2,000 lux, you turn the heating on, the rest of the year, 360 days of the year, there's no electricity and no lighting, no heating. So our mentality was really to think of the Olympics like a housewarming party, but we should be thinking about the house. We should make this building last for a long time. So the great thing about the London Olympics was this ability to build a new park, to look at the mistakes of Athens and a little bit about Sydney. How do you make this a contribution to the society of London? Well, there's an opportunity to build a new park, and with that came this opportunity to develop a new part of London, a socio-economic centre to the east. This is Abercrombie's plan from 43, and hopefully the start of a whole new community of good quality, and to move some wealth, move some money to the east end of London, which is very poor. So the planners had a sort of vision for the Olympics. The Velodrome's there on the left at the top, and that could then become, after the Games, integrated into a new park and a new piece of infrastructure. And the problem with cycling, though, it doesn't make money. It's not like football. We looked at all the previous velodromes. The ones in red, so this is the last 16 Olympics from London in 1948. The red ones have all gone. They've all finished. And in fact, this is what they look like now. Cycling does not generate money, so we had to make this a very cheap place to run. We had to make it affordable. And one of the things we looked at was the 1948 Olympics were in London on this outdoor track. This is sustainable. Everyone cycled or walked there. There's 20,000 people, no roof, no electricity, no cameras. Fantastic. So we like this connection to the landscape, and we didn't want to build a box like this. We wanted a building which felt like it was an open building. So this was my first sketch showing how the cycling on the outside should connect to the inside. We had a brief to provide road, BMX, mountain biking afterwards. And so we designed it to have a split section with glazing in the middle. So for a small event afterwards, you could just use the bottom. But you would have, importantly, this view out between the inside and the outside. And so this ring of glass is between the seats. And our inspiration was that a child in the East End could go into the park, go up to that glass, look in and see the famous cyclists cycling and get inspired. We wanted to connect the city, the East End, to the sport inside, to use this building to inspire people. We did not want a sealed black box. And in most sports buildings are sealed boxes. They don't dictate, they can't tell you what's happening outside. So we worked very hard to control the light conditions, the temperature, to make this connection. And this was the signature of the building, this ring of glass, which allowed you to see inside and out. When the cyclists went in, they loved it, because they train in there all day. And they said, we can go to the top of the banking, and we can look out. We can see the park when we're riding on the track. So they liked it. So we worked very hard on the park. After the games were over, we had this very, very small piece of land, and we put a 1 mile, 1.6 kilometer road circuit in for training. We had the BMX from the games, and we put 7 kilometers of mountain biking in. But it was very difficult because the site was small. We worked very hard with the landscape people to fit this in, use the bridges, go over the river. And we wanted this to be active after the Olympics, to inspire kids to go and cycle, take exercise. And so we worked very closely with the landscape architects, working on the sections, the river, the ecology, how we fitted this in. And so here's the final, the piece, the landscape, the building, the connection between the two. And so this project cost under 1% of the cost of the Olympic Park. So we think it's very good value for money, and it's partly because we used so little material in making it, and it was quick to make. We were ahead of time, and we were under budget. So when we speak to people in the government, we say, was it worth the money? Well, we were very successful in the games, so lots of world records. This was the site before we started. It was a dump for fridges. This is the site afterwards, completely remediated, amazing new landscape, and now it's a very popular place in London. And so we're very, very proud of what we've achieved for the cycling. This was 2 weekends ago, people on the track, people cycling outside. This is what the Olympics can do with the legacy, is provide sport for people very cheaply, at a very high quality. And the government very proudly say that Britain does sustainable design. They're very proud of this, they promote it. But the people in the government were very pleased, especially because we beat France and Germany. I didn't put Italy on there. Didn't want to offend anyone. So we had 10 world records, 24 Olympic records, which is the highest ever in any Olympics. So we're very, very proud of what we achieved. And that's it. Thank you very much.